As you can probably see, this project is going to be a bit bigger than our last toggle box. Our last toggle box was pretty straightforward. We just wired up every button to a separate input on our Arduino and just checked if it was on or off. So no big magic going on or any tricks that we had to do. It was pretty straightforward. For this project though, we're going to use several techniques that we haven't learned yet. That's gonna reduce the amount of pins we need on our boards. But since it's such a big project, we're gonna split these segments up in different videos to make it easier for you to follow along and to focus on each part individually. So on this video, we focused on the LCD screen and on the rotary encoders. How many you're going to use is going to be dependent on how many holes you have on the board. On my board, the micro 3 would be ideal to make life easier. 4 would be possible, but then you need to do some tricks that I'm going to show you how to do them, so that would be no issue. If you want to make your life a little bit easier, I would go for the Arduino Leonardo, just to have a little bit more headroom with the pins and availability, so you don't run out of pins halfway in your project. We're going to be looking at how to wire up several buttons. So in this case, 1, 2, 3, 4, 5 buttons to one input. So that saves you 4 on our old technique. I'm going to show you how to use a shift register, which will make it able to wire up 4 or up to 8 LEDs on 3 inputs. So once again, this is a little trick that's going to help us reduce the amount of pins used on our boards to be able to add more items to it. So those will all be explained in later videos, and everything will be available in the comments down below once it's available and once the video has launched. So if you have any questions, let me know, and I'll hope to see you next time. Thanks. Bye. Hi guys, thanks for watching again. In this series, we're gonna learn how to create our own radio box. As you can see, we have some rotary switches, we have some buttons, we have some LEDs going on, and an LCD screen. I'm gonna show you on our video how it looks in game, so you have some reference. As you can see, if I turn it on the dial, it will actually change on my own LCD screen and in the game itself. I can click on the rotary switch to change from kilohertz to megahertz, switch the channels by pushing the button on the right. And as you can see, we can also change the altimeter's pressure by rotating another knob, and we still have 2 knobs left to record whatever we like. You can see buttons, the lights light up, and they can also turn off again as you like, as you'd prefer. So what do we need for this project? We need a breadboard. We need Arduino. We need a Leonardo or a Pro Micro. In this case, I prefer the Leonardo because it has a bit more pins to work with, so we don't have to jump through too many hoops. We need a rotary encoder. And we need an LCD screen with an I2C module. These can be bought separate or they can be bought attached to the LCD, but as long as they are, as long as you still have both, it's fine. This will reduce the amount of pins needed on the board. Of course, we need a bunch of wires, and as you can see, if you look at the pins on the rotary encoder and the LCD, we need some females to male wires. So that's a pin to a hole on the other side. So usually we use pin, so now we use pin hole, so we can slip them on those connectors and connect them to the breadboard. We also need some normal wires, but you should have those lying around if you're tinkering with Arduinos. So let's get started, shall we? Okay, our Arduino has the same pins as last time. We have some inputs, we have some outputs, we have the power, we have the ground, etc. For our rotary encoder, you can see it uses 5 pins. So it uses the ground, this is the first one. The second one is the positive voltage. The third one will be our switch, because we can press these rotary encoders as a button. Our fourth one will be our data pin, and our last one will be our click pin, which will all be explained later in this video as we go on. As you can see, you can rotate it, push it, and it should all work fine. We also have some pins on our LCD screen. As you can see, we only gonna use 4 pins on the right side, but normally when you wire up an LCD screen, you're gonna use, I'm not good at counting that fast, but I believe it are 16 pins at the top row, which all need to be connected to the Arduino. So we've just saved around 12 pins. So that's worth it by just adding the I2C module, which will connect to the SDA and the SCL pins on our Arduino. They are marked and they have the same name going on, so you would never have to put it in the wrong hole. Okay, so now we've seen our pins, 4 on the rotary, 4 also on the LCD screen. And the data pins will go directly into the board instead of through the bedboard, but we'll see that later on. If you want to use the PROM micro, you have to look out that the SDA and SCL are pins 2 and 3 respectively on the board. So they are marked as SDA and SDL, but they can be used with this board, even though it's not on it. You can also look up the pin layouts on the internet. So if we first start by placing our rotary encoder in our breadboard, just pick some random spot so you have some room left. So as you can see, we have our pins in. From the back you see the holes, and from the front side you actually see the pins going into the board. And the first thing we're going to do is wire up our ground. So we're going to take, I have some short cables laying around, but you can also take a long one. As you can see, the first hole is going to be a ground, and if you flip it around, you of course have to mirror that. So we're going to place it to the ground row, as you can see. So now our ground is connected to our ground row. And we do the same for the power. So now we put in our 5 volts line, and we do it from the second one from the right, if you look at the back of it, to our 5 volts line on the board. So as you can see, those two are wired up. Ground, 5 volts. So we need, in theory, 3 pins more, but first we're going to connect the board to our lines so we get a clear view of what is going on. So once again, as we're used with the toggles, we wire the red wire to the first row to connect the power, and we connect the black wire to our blue row, or the second row, just how you want to call it, to connect to the ground. Pretty straightforward so far. As you can see, only 2 holes have been used yet. And now we're gonna see how we can actually hook up the rest of the pins to our board. And for that we need what? Yeah, mail. Sorry, I had a bit of a brain twizzle, whatever. So here we go. We first gonna wire up the switch, which was the middle. There's a middle, a middle pin. We're gonna use the white wire for it. It doesn't matter which color it is. Oh, I accidentally knocked out the power, but the white wire can go through the second pinhole. So not the second, but marked as 2. So 0, 1, 2. Here we go. We reconnect the power. Our next pin will also be a male-to-male. So we're gonna hook up the data and click pin. And we're going to do that by just putting them in the breadboard and then directly hooking them up to our third hole. So marked as 3, not the third hole. And we do the same for the other one on the 4th hole. And once again, marked as 4 and not the actually 4th hole, because the board starts to count at 0. Yep, here we go. Put the power back in. Let's go. Here we go. Oh no, I'm gonna make it a little bit longer so it sticks in easier. Here we go. And this should do the trick, so now it should stay in. As you can see, we've removed the power cable just to give us some room to tinker around with. And we're going to do the same with the ground, reconnect it. And now we have our first rotary encoder hooked up to the board. We get the power, we get the ground, and we've connected the switches directly to the board, and the 2 pins of the data and the click is going straight to the board as well. So if you want to do the same, you could repeat it with 2, 3, 4 rotary encoders by just wiring up the same, power to the back, ground to the back, and the switch plus the data click cables directly into the board. So if we take our LCD screen, we're going to wire it up as well. Normally we use these pins, but because we've got an I2C module, we can just use the 4 pins on the back. It's going to save us lots of space, and the programming is also a bit easier. So once again, we're going to take the male to female wires because it has those pins. As you can see, the female part is, I don't know who came up with this, but it's a part that slips over the pin. And the male part is the part that gets put in the hole, as you would say it. Then you just have to match the SDA and SCL pins to the SDA and SCL holes on the board, respectively. So as you can see, it's just written on there. SC, the last one was called SCL, and the other one was called SDA. So this is the white one is SDA in this case, which is the second from the right. Here we go. And just as the rotary encoder, we also need some power and ground going to the LCD screen. Let me see. Here we go. It will be the ground, going to the ground. And we still need some power going to our breadboard. And because it's on the top rows, as we remember from last video, it's all connected horizontally. So everything in that row is connected to the board, even though they're that far apart. Here we go. And that's basically it. Our LCD is wired up and our rotary encoder is also wired up. Let's see what happens if we plug in the power. Here we go. And as we can see, the LCD screen is backlit and our rotary encoder is also connected. Nothing's happening yet, but we will see how we can change that in the coding part of this video. So let's get right through it, shall we? Hi guys, okay, we've made it to the programming part of this series, at least of the rotary switch and the I2C display. And just as last time, we're going to need a library. And this time we can just find it in the Arduino IDE itself by going to Tools in the upper bar and click Manage Libraries. And we can search for liquid, crystal, and just press search. And a bit down here is liquid crystal I2C. You also have a version called Gym liquid crystal I2C, but I'm only familiar with this one, so I'm going to use this one. You can install it. I've installed it through zip, but it works the same way. So this is where you can find it, install it, and then we can use it. So how does the library work? Well, first we need to include it. Oh, there you go. Capital L, liquid, capital C, crystal underscore capital I to C dot H. Closing bracket. And this library needs a default library that's already included in the IDE called wire.h. So that's our first step. Now we're going to define our screen. So we're going to say liquid crystal underscore I2C, just the name of the library and how they call the type of the LCD screen. So we're just going to call it LCD is a liquid crystal underscore I2C. Now I'm going to type a line and I'm going to explain it afterwards. 16 to close it and end the line. What this part says is that we're going to create a liquid crystal I2C screen. So he knows, the system knows what kind of device is connected to your machine. Here we're going to say where it's connected. So in this particular case, it's the SDA and SCL pins, and they have an address in memory. You can look it up through some apps that run through your Arduino to see which devices are connected on which address, but normally this is the default address that you can just use. 16 and 2 are referring to the amount of characters per line and the amount of lines. So our screen can output 16 characters on 2 different lines. So 32 in total. And once again, if there's something you don't understand or you have some questions or I go over too fast, please let me know and I will get back to you as soon as possible. The code will also be available in the description below. So let's take a look at how a rotary encoder actually looks signal-wise. We have a pin A and a pin B. In our case, it's called the CLK and the data pin. And inside the mechanism, there is a way to see which pin or which direction you're turning by defining which pin gets hit first by which pulse. So in this case, signal pin A gets hit first, then signal pin B. If you know that it turns the other way, then signal pin B gets hit first and signal pin A gets hit second. So that's a bit the technical side behind it. You don't need it if you don't want to know it, but just to give you some background on how it works. So in our case, in our code, we need to do something with our pins. So we do rotary 1, pin A. And once again, these names are just something I come up with. If you have something better in mind that suits your process better, like pin or rotating 1 encoder, whatever, it's all up to you. But we're going for pin, and it's connected on the third input. We have rotary 1 pin B, which is connected to the fourth input on the Arduino board. And just to be precise, we also have rotary 1 switch, because ours actually come with a switch, not all do, but it's optional. So now we set on the Arduino, our pin A is connected to the 3rd hole, and our pin B is connected to the 4th hole. And our switch is connected to the 2nd, etc. So we want something to keep track of, or to give us a visual update whether it's turning and which side is turning, etc. So we're going to initiate a counter. And once again, we're using ints. And ints mean that it's going to be a whole number. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And it will never be 0.5, 0.6, 1.8, etc. Okay. Now to know which side it's turning, we first need to know on which side the pulse is going right now. We leave them blank because we don't know that yet. And we need to know, well, if it's now at high because the pulse is coming in, what was it last time? Was it low or was it high as well? Because if it was high as well, nothing has changed. A last state. So we have A, the state right now, and A, the state it was before. We're going to define our pin modes again. So rotary 1 pin A is an input. This has to be a comma. And rotary pin B, it's also an input. And we have a switch. Rotary 1 switch is an input pull-up. The difference between these is that these will give a specific signal to a wire on the board through a special process. The input pull-up is nothing more than a switch that gets its power through the 5 volts, gets pulled up, power goes back to the board through how do you call it? A wire. In this case, our switch 2, and the system knows, okay, it's been on. That's it. Nothing more, nothing special, no magic, electrical wonders, etc. Just plain old. Okay, we have our LCD. We're gonna start it up. And once we started it up, oof, gee, backlight is on. Once again, these codes are derived from our library. So because we've included it, the system knows, okay, we've set init. So initiate, in this case, somewhere in the library is some code that says, okay, let's initiate and I need to do this, etc. So you don't have to code the entire block. You just use the code that they've already written for you to take off the burden and make life a bit easier. And we're going to start our checking by defining the last state. It's digital read rotary 1 pin A. So what do we say? Okay, setup gets run when you boot the device and the program is loaded, etc. It's going to check, okay, but what's the state now? So every time we check something, in the next steps will be towards this value, or at least this will be the base value. So we're going to read rotary pin A, so we know the system knows it's hole 3, pin 3, and we're going to store the state of this in a last state. So it's going to be high or low, so 0 or 1. And in the last video, I went a bit more deeper inside the setup and how the loop block works. But if I have to summarize, it's the void setup gets run at startup, like when you first plug in the device, code is loaded on, etc. And the loop part is loaded, is executed every time, repeatedly, to check parameters, to check states, to see what our system is doing, etc. Okay, so what are we gonna do in the loop part? We're gonna say our A state is digital read rotary 1 pin A. So now we have our last state initiated here and our A state initiated here. So we know these should be the same if you first started them. We're going to create an if statement. What's an if statement? An if statement is a code block that gets executed if the statement between brackets is correct. So in this case, if digital read rotary 1 pin B is not equal, so if it would be like this or this, it would be equal. And if we put an exclamation mark, is means not equal to A state. So if the pin B is not equal to A state, so if something changed, we know that it turned clockwise. And if it's the other way around, like if it's any other case, in this case it means it turns counterclockwise. So here we have a counter which is 0, plus plus adds 1, minus minus deducts 1. So this would mean that in this case, if it goes counterclockwise, we just add 1, add 1, add 1 for every step. And if we go counterclockwise, we deduct 1 every step. So pretty straightforward. We can actually, just to give you a visual representation, we can do serial begin. And every time it gets updated, we do serial print counter. So if we plug in our Arduino, always make sure that the right COM port is selected. Upload. We can actually see what is happening by opening our serial monitor. Oh, here we go. Oh, I unplugged the wire. My bad. So I have to reopen it. Oh, here we go. I have a short somewhere in my circuit, so that's why this is happening. Oops. Okay, guys, I'm sorry. I've forgotten something before we go back to the serial monitor. We have to check, of course, that if the A state, so the current state of A, is not equal to a last state, then we do everything we've just programmed. Let's move this up a bit, just have a better overview. So what we've forgotten is this part. And why is this important? Because here we said, okay, when we set up, the last state is this. And then we save every time the program runs, it says, okay, but what's a state now? And as long as these are equal, nothing has changed, right? So if something changes, so if a state is different than a last state, we know that something has changed. So that's when we're going to execute the code, or else it's just going to spew out values and numbers in a continuous state. And in our code, we can actually see that we've created an if statement. So if this, do this. But inside our if statement, we've actually nested another if statement. So if this is true, and then it's going to check, okay, but if this is true, I'm going to do this, or else I'm going to do this. So if we upload this to our Arduino, okay, it's empty when you look at the serial monitor. But if we turn it, you can see it goes up. And if I turn it the other way, oh, it's stuck. So you can see we're going that way. I think this rotary encoder is a little bit, I've used this for something else, so I think I've ruined it, but the concept works. You see, if we go one way, it goes up. If we go the other way, it goes down. Big increments though, but that happens. Sometimes things break. Okay, so this works. But we can also write this to our cursor 0.0. What this line says is our LCD screen and set the cursor. So that just means where are we going to write our line? Well, we're going to write it on the first row and the first character. So we had 16 characters in total, 2 rows. The first row is called 0, the second row is called 1. So we're just going to do start in the far left corner with our message, and our message is going to be lcd.print counter. So every time our counter changes, our LCD screen will print the new value. And we can do the same if it turns the other way. We could also just take it all out and place it outside of this block. You might wonder why. Because if we take a look at our code and how the flow will be, is it's going to check if something has changed. So in this case, we know if something changed to this, if this changed to that. But the block, the if statement, runs still here. So everything after these two sentences gets run every time. So the set cursor will run every time something changes, and the print will run every time something changes inside of these two blocks. So, or else we could do this, but then you have, see, your code gets bigger because you have it in 2 places and the process is still always the same. So we can just put it outside of the block to keep it a bit tidier, especially if the code will be a lot longer and bigger. This will make things a bit easier. Okay. And we're going to say a last state is equal to a state. So if something changes, we do this, and then we go back to saving it in our last state. So then next time we can check, okay, what has changed? Is something changing? Etc. And to keep it informed. I think perhaps this is the line that's going to balance things out a bit. Yeah, see, a lot smoother. I keep pulling the wires out because they're not in properly, but the concept works. My computer is stuck. Well,